One of the problems in physics during the early times was the speed of light. They did not know how fast light traveled. Some assumed that it is infinite and cannot be measured, while some argued that it has to be finite. But did you know that such an important discovery in science was in fact an accident? Until the end of the 15th century, sailors navigated with almost daily reference to land. In the Mediterranean, it was difficult to go very far astray, and in Western and Northwest Europe, navigation was coastal. Ships hugged the shore from Gibraltar to Norway and the Baltic. Voyages beyond Europe became difficult without proper navigation. This is the point where sailors started relying more on the position of stars and sun to know one's position on Earth, for which they had to imagine themselves on a grid of lines on the planet to pinpoint one's location, the latitude and the longitude lines. Latitudes are the horizontal lines that run along the equator to the poles. Or in other words, it tells you how north or south you are relative to the equator. Longitudes are the vertical lines joining the two poles. It tells you how east or west you are from the line dividing the earth, called the Greenwich. Latitudes were easier for sailors to determine using the position of stars and sun. For example, if you stand at the North Pole and locate the North Star, it will be directly above your head. Similarly, if you are at the equator, it will be 0 degrees to you, basically at the horizon. So by knowing the angle of the North Star, one can find the latitude. But finding longitude was not that simple, because there is no fixed position of stars as a reference point. Because as Earth rotates in its axis, so does all the stars. Longitude can also be translated as the local time. How? Determining how much east or west you are can be translated to how much of Earth's rotation are you from another point. For example, at 0 degree longitude, if it's midnight, if you are in a place whose time is 9 pm, which means you are at 45 degrees west of 0 degree, which is the Greenwich, as every hour corresponds to 15 degrees of Earth's rotation. But for this method to work, you need to know the time in two locations accurately when you're drifting in the middle of the ocean. So how will you know this? In 1612, Galileo for the first time observed an eclipse of a satellite of Jupiter. Such astronomical events were, for practical purposes, instantaneous events useful for navigation. For example, Io orbits Jupiter once every 1.76 Earth days. Galileo understood that if we can draw tables of such events and putting down the time of such events at various places on Earth, then a navigator on the high seas could note the local time of such an eclipse and compare it with the local time at which it was predicted to happen at the reference location. The difference in times could therefore give the longitude. As ingenious as it may be, the method did not bear fruit due to lack of powerful telescopes to carry on voyages and also because of inaccuracies with the charts drawn. Almost nearly a century later, in 1676, long after Galileo's death, such charts were still in making and were in need of perfection. Danish astronomer Ole Rohmer was trying to draw such a chart by timing the eclipses of Jupiter by Io. By timing eclipses over numerous years, he observed a peculiar pattern. The time interval between successive eclipses shortened as Earth moved closer to Jupiter in its orbit and lengthened as Earth moved away. Based on his data, Rohmer estimated that when Earth was nearest to Jupiter, eclipses of Io would occur approximately 11 minutes earlier. Conversely, 6.5 months later, when Earth was farthest from Jupiter, the eclipses would occur about 11 minutes later than predicted. In a stroke of brilliance, he realized that the discrepancy in Io's eclipse timings was a result of the finite speed of light. In essence, when Earth and Jupiter were on opposite sides of the Sun, light from Jupiter had to travel a longer distance to reach Earth than when they were closer together, and this can only be explained by the finite speed of light. He approximated that it took around 22 minutes for light to traverse the diameter of Earth's orbit. This time period was an error and later corrected as 16.7 minutes. So by dividing the diameter of Earth's orbit around Jupiter and by the time difference, the speed of light is calculated to be 186,000 miles per second, the fastest object in the universe.